Now let's look into the example of our fitness landscape. So in this example we are interested in constructing a fitness landscape based on a very simple problem that we want to solve. Therefore, please open the file fitness landscape example. That's an example file from David Rutten, therefore it's example Rutten. And the idea of this file, if you open the Grasshopper file, is that we have two curves. Here the green one and the second one marked in green. And we are interested in finding the shortest distance between the two curves. So these curves are three-dimensional curves somewhere in the 3D space. So it's not clear, or they have no intersection points. Okay, what we do, we have these two curves and we divide them into equally distant or into equal segments. We have 80 points per line that we create, and for one of the lines, the points we create, we graft them into a tree, so we can measure or we can draw lines from each point to each point, or from each point of line A to all the other points of line B. So a pairwise comparison or a pairwise measurement of the length of these lines. So we draw lines from all possible pairs of points on line A and line B. And then we measure the length, and these lengths, they are put into this fitness landscape component that we have here. So we can find this component here in the parameter panel under utilities. That's the fitness landscape component. And this takes basically the values. These are the values that characterize the fitness landscape. And here we have the number of iterations on X and Y on this landscape. These are our counting parameters. This is the counting value, how often we divided each line. And finally, we have the bounding rectangle that we draw in Grasshopper. And if we activate the preview, we find here this beautiful three-dimensional landscape. That's our fitness landscape. And if you have a look at the lines that we created here, so you cannot see them very well, but you see these are a lot of lines from all points to all points. Kind of the preview. And what's mapped in this landscape is, on the X and Y direction, all possible distances from line A, which is, for example, the X coordinate of this rectangle, and all points from rectangle B. And in this landscape here, for example, we have a very short distance, so the values are small. And here on the edge, we have very long distances from this point, from line A to line B. So here we map all the possible distances, kind of a distance matrix for all distances of the points that we created on the lines. And now we look at it just to understand the idea of a fitness landscape. Of course, we can use it to identify the areas where we have the smallest distances or the best solutions, metaphorically. But here we have the lines, the shortest lines between the two curves. So this is here are the optima. And we could also filter them out of the generated lines, so we could now take them out of all possible variants that we've generated. But often it's not possible to generate all possible solutions, and also here we have used a certain step size to iterate through these possible points. If we would take continuous numbers, we would have theoretically an endless amount of possibilities. If we would have very, very small floating point numbers. But if we assume that the landscape is continuous, we have now also, by the interpolation between the measured lengths, all the other lengths, because we know the problem is continuous. Here the problem can be analyzed very well, and you can make a kind of a meaningful brute force. Means you can generate all possible variants or all meaningful possible variants and just selecting the best one.